everyone, welcome back to my AIGP study guide series. In the last video, we explored what autonomy looks like in AI, from simple decision making to full system independence. We also discussed the importance of human oversight, which the IAPP defines as the process of effectively monitoring and supervising an AI system to minimize risks, ensure regulatory compliance, and uphold responsible practices. But there's more to autonomy than just making decisions. The real shift happens in how AI systems learn. In this video, we'll continue to answer the question, if traditional AI already had elements of automated learning, what changed in modern AI that made learning truly autonomous? And to get there, we're going to start with a deceptively small idea: features, and who picks them. In traditional machine learning, humans had to decide which features were important. This process is called feature engineering. Feature engineering is formally described as the process of manually extracting relevant features from raw data to be used as inputs for a model. One example is the Gabor kernel, or Gabor filter, widely used in image processing and computer vision. A Gabor kernel is a small matrix, essentially a tiny window of weights, that slides across an image, performing mathematical operations on pixels to detect patterns like edges, textures, or orientations. To use a Gabor filter, you must first generate the kernel using a formula and a set of tunable parameters. The IAPP defines parameters as the internal variables an algorithmic model learns from the training data. They are values the model adjusts to during the training process so it can make predictions on new data. Parameters are specific to the architecture of the model. For example, in neural networks, parameters are the weights of each neuron in the network. In the case of the Gabor filter, the main parameters include lambda, theta, phi, sigma, and gamma. Now, you don't have to understand what these parameters mean. Just know by adjusting these values, you can emphasize or suppress certain edges or textures in an image. For instance, setting theta to equal pi over 2 emphasizes horizontal features, while setting theta to pi emphasizes vertical ones. Once the kernel is defined, it's convolved over an image, meaning it slides across every region. At each step, the dot product between the kernel and the local patch of pixels yields a single value, indicating how strongly that region matches the pattern. We'll unpack what the dot product means shortly. For now, just know that this operation yields a feature map, which is a new image that highlights the detected features. But crucially, this entire process is manual. Humans decide which filters to use, which parameters to adjust, and which outputs matter, making it a clear example of handcrafted feature engineering. In contrast, modern AI systems like neural networks learn these filters on their own. Instead of manually specifying edges or textures to look for, the model takes in raw data, like pixel values, and turns them into edges, then shapes, then full objects like faces, all without being told what to look for. So what are features? Features, also known as variables, are the individual pieces of information we use to represent each data point. For example, features could be jawline width, hair length, and facial hair. The IAPP defines variables in the context of machine learning as a measurable attribute, characteristic, or unit that can take on different values. Variables can be numerical or quantitative, or categorical and qualitative. And these features come from each one of our training examples, which is represented by a feature vector. A feature vector is a list or array of values that describe an input. So each training example is typically one feature vector, and your data set is the collection of many such vectors. Before we continue, let's jump into some quick math just to understand why it's referred to as a vector. It's called a vector because mathematically, the features form a point in n-dimensional space, where n is the number of features. With each additional feature, we add a new axis. So if we have 2 features, we can plot it on a 2D graph. If we add a third, our vector will now live in a 3D space. This aligns with the concept of a vector in linear algebra, which is an ordered set of numbers. Let's start simple. Think of a vector like an arrow. It has length, how long the arrow is, and direction, which way it points. So if someone gives you the point 3, 4, you can think of a vector as an arrow that starts at the origin, 0, 0, and ends at that point. In math, a vector is also just a list of numbers telling you how far to move in each direction, x, y, and z, etc. A vector isn't just a point, it's like a set of instructions that tells you where to go. Now let's take that a step further. A unit vector is a vector with the length equal to 1. It keeps only the direction and strips away the size. Unit vectors by themselves don't tell us how to build space. aka form a coordinate system. That's where basis vectors come in. A basis is a set of vectors that can be combined to form any vector in that space. Even better, if the basis vectors are both unit length and perpendicular, we can call that an orthonormal basis. That is the gold standard. Linearly independent, spans the space, and each vector is exactly 1 unit long. Also, when each pair of vectors has a degree of 90, their dot product equals 0. But we'll tackle that in a bit. First, what does it mean to span the space? It means you can combine the basis vectors, scaled by some numbers, to reach any point in that space. Let's say you want to build a new vector named C by combining vectors A and B. To scale a vector means you multiply x by the vector A. So in this case, if x equals 2, then x multiplied by a is 4, 2. Scaling a means you move along the line, forward or backward, longer or shorter, depending on the x. We can do the same thing with y for b to get 1, 2. Now, if you imagine you're starting at the origin, 0, 0, first you travel along a, scaled by x. Then from wherever you landed, you travel along b, scaled by y. This is called vector addition. Doing so gives us our final location, which is 5, 4, and that is the vector C. This means if A and B point in different directions, then by combining them, you can reach anywhere on the plane, just with different choices of x and y. This is what it means to span the space with linearly independent vectors. But if they point in the same direction, you're stuck on a line, no matter how much you scale them. Now let's move from vector addition to something totally different, yet related, the dot product. You can think of the dot product as directional multiplication. So we care about movement in the same direction. And the goal of the dot product is to track similar components. The dot product returns a scalar that tells us how much stronger we've made the original vector. For example, what does 3 times 4 mean? When dealing with simple growth rates, multiplication scales one rate by the other. 3 times 4 can mean take your 3 times growth, make it 4 times as large to get 12 times. Think of quantity like scaled overlap. The dot product is a type of scaling that takes overlap into account. We're allowing the amount of overlap to be scaled by the size of the vectors. That's why we use unit vectors with the length of 1. That way, when we use the unit vectors, the overlap is just a percentage. We also have to consider the direction of the vectors. Like I said, the dot product is like applying the directional growth of one vector to another. The result is how much stronger we've made the original vector, positive, negative, or 0. Now, let's say the number 3 is the directional growth in a single dimension, the x-axis. Let's say this 3 means triple your bananas, and 4 is the directional growth in the y-axis, and here it means quadruple your oranges. As you can see from the graph, clearly no part of either vector is aligned with the other. And if we end up doing the math, we'll see the dot product equals 0. You're applying a rule that scales oranges to a vector that only has bananas. The result? Nothing. This is application, not addition. With vector addition, the coordinates 3, 0 plus 0, 4 equals 3, 4, a new direction. But with application, the second vector modifies the first. And if they don't align, there's no contribution. Think of it as how much push is one vector giving to the other. We can also visualize it like a Mario Kart boost pad. The red vector is your direction and speed. The blue vector is the direction the boost pad is facing. If you're going 0 miles per hour, you get nothing. If you cross the pad at a 90-degree angle, again, no boost. But if you hit it head on, your x speed and the y speed both contribute to the boost. That is what the dot product tells you. How much of your speed aligns with the pad's direction? The dot product doesn't give you a new direction. It gives you a way to compare the two vectors with a scalar, a single number, telling you how much one vector points in the direction of the other. For example, if A equals 3, 1, go 3 right, 1 up. If B equals 2, 4, go 2 right, 4 up. The dot product is 3 times 2 plus 1 times 4. Adding those overlaps gives you 10. That number is your alignment score, a scalar that tells us how much are you pulling together and in what direction. We're not adding magnitudes, we're measuring how well two vectors match, dimension by dimension. That's what the multiplication captures. It emphasizes agreement and it emphasizes directional match. So enough math. How does this relate to machine learning? In early image recognition, we could extract human interpretable features like jawline width and hair length because early models like the perceptron couldn't discover features on their own. They relied on hand-picked inputs and learned how to weigh them using a simple update rule. The features are fed into the model during training through labeled data. Input features paired with the correct output, the label. So the label data is where the features live or exist. That's how AI is introduced to which features to focus on. Each of these features actually becomes one dimension. And each training example, say a photo of a labeled male or female, would be a row of feature values or inputs paired with a label, like male or female. The training example would become a feature vector in that space. So if you extract, say, 3 features per image, each training example is plotted in 3D space. So if you extract 100 features, that example lives in a 100-dimensional space. That's what we mean when we say each feature vector is a position in high-dimensional space. Each feature, or X value, is a coordinate on its own axis. Together, they describe a single point in space shaped by those features. And that label, male or female, is the Y value the model is trying to learn to predict. During training, the perceptron uses the perceptron learning algorithm to update its weights. If the model makes a correct prediction, the weights stay the same. To make a prediction, the model then multiplies the input vector by the weight vector to get the scalar, or the dot product. And that will give us the predicted output. The scalar represents how aligned the input feature is with the learned weight. You can think of the weight vector as representing the ideal version of a certain class. If the input vector points in a similar direction, the dot product is large and positive. That means high alignment, and it likely belongs to class 1. If it returns a negative dot product, the opposite direction, it likely belongs to class 0. That scalar is then passed through a simple activation function to decide the final output. Therefore, the scalar is a number that tells the model how well the training example aligns with the learned concept. No features are discovered automatically in traditional models like the single-layer perceptron. It's about humans choosing which aspects of the input to emphasize. So what we've just described is called feature engineering. We tell the model what features are important, and the model's job is just to learn how to weigh those features. But modern AI uses feature learning. Today's models don't just learn from features, they learn the features themselves. Let's break that down. Imagine showing a neural network thousands of photos, but instead of telling what to focus on, you just give it raw pixels. At first, it only sees the numbers, the brightness values of each pixel. But over time, it trains on examples. Patterns begin to emerge. The first layer might learn to recognize simple shapes, horizontal lines, vertical edges, diagonal strokes. The next layer builds on that, finding corners, curves, and outlines. Then comes some more abstract features, like noses, mouths, or eyes. And eventually, the network learns entire concepts like, this looks like a face, or this resembles a dog. At no point did a human define those features. The model discovered them by learning which patterns were useful for making accurate predictions. This process is called autonomous feature learning, and it's what powers modern deep learning systems. In short, traditional AI learned from human-designed features. Modern AI learns how to create features themselves. And that's a major step forward in autonomy. Not just acting independently, but understanding the data without human guidance. Today we saw that autonomy in AI isn't just about making decisions. It's also about the way AI learns. Modern systems no longer have to rely on handcrafted features. They learn directly from raw data, discovering patterns without explicit guidance. In the next video, we'll take that idea even farther. If AI can choose its own features, does it still need clean labeled data? We'll explore how deep learning models can learn from messy, unlabeled, and incomplete data sets and still find structure. Along the way, we'll introduce self-supervised learning, reinforcement learning, and transfer learning, all to continue answering the core question, how does the definition of machine learning differ from traditional to modern AI? Thanks again so much for watching this video. Like always, if you have any questions or suggestions, leave a comment below and I'll do my best to get to it. Otherwise, I'll see you in the next one. Bye!